Alright, so today we continue with ISRs. We focus on timer 0. Next lecture we'll talk about timer 1 and timer 2 as well. And we start to talk a bit more about task-based programming and what's going on here. So let's first talk about timer 0, and if you look at the data sheet you see this particular layout, and there's a lot of components, and actually the first thing that you may see is that your timer 0 is actually quite a complex hardware unit that you can do a lot with. There's a counter that's the core of timer 0. But there are some comparators that you can see here. There are some registers that you can compare with. Hardware interrupts can be generated according to those, and things can then start. There's waveform generation. You can create PWM signals out of this as well, that we will be talking about next block. So there's a lot going on. Now let's have a look at this slightly more simplified picture, where you see the core components that build your timer. So the first thing is that your timer is being clocked. So that you have this counter, and it's a register, right? So the register moves forward from 0 to 1 to 2 to 3 to 4 until 255, and it loops back to 0, and it keeps on going. It keeps on counting. So the rate at which that is happening is determined by the clock signal that you would like it to give. So you have some choices. One is that you can use the internal clock, and that can be divided in several ways. There's a bunch of options. So if you want to go at the clock speed of your processor, you divide by 1. If you want to go a little bit slower, you divide by 8. And depending on which clock signal you're interested in, there's also an external clock that you could feed in. Depending on which one you choose, you will actually increment this at a certain rate. So the idea is that you can program in a control register for your timer 0, which through these positions that are in that register, which prescaler you're going to set. So for example 1864, we are not going to use the external clock, or we do not connect an external clock to this, but you have a choice, and that's going to be very important. We'll do a few calculations along the way. Now that counter is going to be incremented, and you can compare it to some register that you can set to a certain value. Say I'm setting it to 124. That is one of the examples that we'll be discussing. Then if this particular counter reaches 124, then this compares, and that may trigger some kind of a hardware event. Depending on other control registers, you may reset this particular counter as a result of that comparison, or do other things. And you also have a second register, again with the comparator functionality, and when those two are equal, again there may be some hardware interrupts that you can set up in interrupt service routine, and so on and so on. Now, and also as a result of the comparison, by the way, you can also influence like a channel, like a PWM signal that is low and then goes high and then low again. Well, depending on when you see the comparison, you may go from high to low, and then later on when this is back to 0, you go say from low to high again, and so on. But we'll talk about that later. Now for the clock functionality, we're very much interested in this counter because it can help us to build also a software clock, as we will see in a moment. But so what is the idea that we want to use is that we use that counter and compare it to this register called OCR0A, and if it compares on equality, that's how we will be setting it up. We're going to clear this particular counter. It goes back to 0. Say this particular value may be 124, and then when then the counter goes back from 124 back to 0 and then starts counting again to 1, 2, 3, 4 and so on. Now, we can set an interrupt flag that gets triggered, right, when this comparison holds, and it will make, if you have enabled the interrupt that corresponds to that, will make your program counter jump to that corresponding code that has your interrupt service routine. Now, and then what I said is you can toggle the I/O line, which is this channel A, and you can create some kind of a waveform. Now, we can also compare TC and T0 and OCR0B, and the only exception is that you cannot clear TC and T0. That's not an option given to you by the hardware. So, as I said, channels A and B can be used for PWM. Now, yeah, sure.
For PWM, is that like, do computer fans use the same thing? Because I'm pretty sure like a lot of fans are PWM controlled.
Sorry?
For computer case fans, I'm pretty sure they're PWM controlled, so like are they?
So the question is, what about, say generally a fan, for example, that spins around? That's really a motor, right, that spins around. We will come to that much later into the course. But you need to sort of set the control, the motor with a specific type of signal that tells it to run it at a certain speed, for example. Things like that can be done.
So what are these registers up here, the TCN, T0, and the OCR0A?
Yeah.
What do each of them do, and how are we going to use them?
So the TCNT0 is a counter, and the counter goes from 0 to 1 to 3, 0 to 1 to 2 to 3 to 4, and it's clocked, so it happens at a regular rate. So this is your timer 0, and it's just a register that you can even read. You can use it in your program by reading it. But the point is that that register goes from 0 to 1 to 2 to 3 to 4, depending on the speed at which you wanted that to happen. And that you can set using these bits, where this mux then selects which clock rate you will use according to this divider. Now, this particular register is just a register that you can set so that when those are the same, then a hardware event will be created, and then something can happen. So what would you like it to happen? Well, for example, you may want to generate a PWM signal that we're just talking about, where upon comparison you swap from high to low. On comparison you can also say, I would like to clear this thing to back to 0. On comparison I can also say, I would like an interrupt service routine to get triggered.
So does that register OCR0A, does that contain the instruction or the point which you're comparing to?
OCR0A is a register that contains a value, like say 124, and when this reaches 124, then there's equality, and that will trigger a hardware event. Yeah.
So that's the point.
Mm-hmm.
That's the point you measure.
Yeah, exactly. So, if we're looking at programming this hardware device, right, we have a bunch of control registers. So that's what we're going to talk about, because those are the ones that you're going to program yourself. So we have the TCCR0A, TCCR0B, and so on. And you will see in the datasheet that they are labeled with those keywords. Remember again, right? These keywords are just equal to constants, right? And I'm interested in, say, this particular position. Now, what I'm interested in actually is these WGM01, 00, and 02. They are stored in both these registers. And they actually tell you what kind of waveform generation mode you will set. We will come to that in a moment. That's the next slide. And at the same time, I have my CS00, CS01, and CS02. And if we look back at the previous slide, those are the positions in this register that set the mux. So those can be used to figure out or to set what kind of prescaler you're going to use. That's what it is called. And it controls now which clock signal will push through to increment the TC and TC zero counter at what rate that will happen. So here are those two tables. So definitely look at the data sheet to see how that all works. Now here you see what kind of waveforms you may have. So there's a whole bunch of choices. Right now we're only talking about this particular one. When we talk about PWM, we will talk about some other possibilities. But this is generally used for when we want to create a software clock. So what does this mean? You see a few columns, right? So there's a mode of operation, it has a certain label, it's explained of course in the data sheet and explained here in the text. There's a top value that is set at, that you can set in OCR8, that is that one register that we were just talking about, and so forth. Now, I'm not going through all the details here, but the point is that the waveform generation mode for this particular item here sets an auto clear of that counter that we're just talking about, the TC-NTC0, on matching the OCR0A. So how do you make sure that that happens? Well, you need to set the position corresponding to WGM01, right, with this particular position. You want that particular bit to be set to 1. So I left shift again over these many positions, and then I essentially OR a 1 at that particular position into this register, making sure that this becomes a 1. So it's the same type of computations that you have been doing before, right? So now the TCNT0 increments to OCR0A is now reset back to 0, right, this particular counter, and starts incrementing again. So what will you see? You will see kind of a sawtooth behavior. Like TCNT0 over time, if this is the time axis, right, goes from 0 to 1 to all the way to OCR0A, goes down to 0, slowly increments again to OCR0A, goes immediately back to 0, and you get this sawtooth. So now every increment of TCNT0 is clocked using the FCPU, which is the clock speed of your CPU, right, divided by the prescaler that you can set by using those 3 positions in this register. Now, here you see what happens. For example, if I want to divide by 8, then I need to set CS01 to 1, that particular position in that register. So, for example, I'm actually setting it to 2, meaning that if you look at the previous slide, then I will have the bit interpretation 0, 1, 0, all 0. So I'll set this particular one to 1, and those stay at 0. And that will give you this particular setting. As you can see, I mix and match different ways of programming these registers. I like you to sort of become fluent in the different kinds of ways that you can do it, and you can choose the one that fits you the best. Now, each TCNT0 increments now, so how much time does that take? Well, we have a prescaler of 8, and suppose we assume for this lecture that you have a 1 megahertz clock, then 8 divided by 1 megahertz gives you 8 microseconds. So it takes, so exactly after 8 microseconds, I increment the hardware, right, increments this particular counter. So it goes from 0 to 1 in 8 microseconds, then to 2 in 8 microseconds, and so on. And so if I'm setting my OCR0A to 124, I see the following transitions happen. 0 to 1, 1 to 2, 123 to 124, and now I'll go back from 124 to 0. So how many transitions do we have? We have 124 plus 1, because I go back to 0 here. So we have 125 transitions, so we have 125 times 8 microseconds that it takes to reach this particular value for the counter. So after this it goes back to 0, and then goes up 1, 2, 3, 4 to 124, goes back to 0, and so on. You have the sawtooth behavior, and one sawtooth is now taking 125 times 8 microseconds, which is 8 milliseconds. So it's kind of interesting. So I can now also do maybe an interrupt service routine that says, hey, when I'm hitting that particular register value of OCR0A in my counter, then I can do something special. So every 1 millisecond that ISR will then be triggered, and I can create my own software counter out of that. I can create my own clock with an accuracy of 1 millisecond, which is really cool, because now all of a sudden I can start for example, replacing all my delay functionalities and so on. So enabling an ISR every period can now be used to create a precise 1 millisecond clock. So what do we need to do first? We need to enable the interrupt. So there's a mask register called the interrupt mask register, as this name, the TIMSK0. And it has a bunch of interrupt enables here that you can set. So each of those 3 can correspond to an interrupt service routine. The first is a certain kind of interrupt enable, where if timer 0 overflows the interrupt, if timer 0 overflows, meaning that it goes to 255, it's a register of 8 bits and then it goes back to 0, then at the moment that it overflows, you could create an interrupt if you want to. Now, if you have this compare match, right, then you may want to set this particular position to the bit on this position to be 1, and that will then allow you to catch that event in an interrupt service routine, and in that interrupt service routine you could create, for example, an update on your software task timer. Now this becomes a software counter. So initially we have a global variable that we set to 0, and every single time that this guy gets triggered, this particular task timer is going to increment. And how often does it happen? Every 1 millisecond exactly. So I can always now rely on a global variable in my own main code or in other tasks to figure out how much time has lapsed and so on. I can just look at that particular software variable, our global variable over here, and do things like measuring the amount of time that lapsed before I push the button, or like the stopwatch type of tasks that we will be talking about, and so on. So that is what we see happening over here. So we'll put it together in a piece of code in a moment. But the cool thing is that we now have a reliable clock that we can use in our software that increments every 1 millisecond. So let's do an example. I like to toggle the LED every half a second. So how many of those increments do I need? I need 500. So if this task timer equals 500, then I can toggle it, and then I reset it back to 0. Oh, this is actually wrong. It should be just a single equal sign. I can reset it back to 0, and then it starts counting again from 0 all the way up to 500, and then this condition is met in my main while loop. I'll toggle it again. So now I can toggle at a really accurate 1 Hz signal, which is beautiful. Now, that is what you could do. So now this avoids any blocking delay functionality. Rather than saying I'm going to wait for, say, half a second and then I toggle, and then I wait again for half a second and then I toggle. During those half-second wait times originally programmed through the delay functionality, I can now do all kinds of other stuff. So there's one problem though, and maybe you can see that. What happens if in your main loop, right, I actually have my, at some point my task timer gets to 500, but I've not yet reached this particular if statement, and this task timer already increments to 501. If that happens, then this equality will never happen, and I will never toggle that thing, and things will actually go wrong. So a better way to program this is to do it slightly different, and to have a task timer that goes that counts down. You can do it in, there are other solutions, but this is the one that I like the most. It's nice and elegant. I now initialize my task time to 500, and in this interrupt service routine that triggers every 1 millisecond, I'm going to decrement this task timer. And I'll do that as long as this is larger than 0, meaning that it will get stuck at 0, it will not go below 0 after that. And it means that in my main while loop, that if the software task timer equals 0, it will remain 0 until I execute this if statement. So I will definitely execute this if statement. I execute my task, like toggling the LED, and then I reset my software task timer back to the task time. Great. So here we see the initialization of the timer. So what did we talk about in the previous slides? We have this 8 control register, right, the TCCR0A. We want to set the waveform, which allows us to create that sawtooth behavior where the top of the sawtooth is at 124. This leads us to 125 transitions in a single sawtooth, and we saw that would be 1 millisecond, because every single transition is going to be taking 8 microseconds, because we do not clock it off our original clock frequency of the CPU, but we divide it by 8 by setting this particular register to 2, meaning that the prescaler, the divider of the clock, is set to 8. We can do 64, we can do other numbers. And then we also want to enable the interrupt that will call this particular interrupt service routine. So this is our initialization procedure. So when we look at the main style of programming, we see that we first want to initialize all our registers, then we enable the global interrupts with our macro, and now we have the while loop that has these types of if statements. When this condition is met, I execute the task, and this task is now executed every single 1 millisecond. So that is actually task-based programming, and we can add many more of those if statements and make this while loop much more, you can add much more to this if you want to. Yeah?
Do those registers need to be initialized at all, or if you just include that in your code, the machine will recognize it?
No, you don't have to initialize those. Those are already for you present. Those are, you can treat them as variables, as if they are already initialized. So you don't have to initialize those. As a matter of fact, they also have default values. For example, this particular guy is an initial value of all 0. But there are other registers that have maybe a default value where some of these bits are actually equal to 1. So we can look that up in the data sheet, what the initial value will be, or the default value.
Do they have a data type?
These are registers, so you can treat them, you can manipulate them the way we do it over here. So, you can treat them as hexadecimal numbers, 0x. So you can assign to this, for example, 0xAB, and then it will get the 8-bit value of AB, or 0B, and then 801 bits. Or you can give it an integer that will be represented as this will be transformed into a bit representation, and that is what the register will get. So those are all the possibilities that you can do.
So So we wouldn't have to put that as a function. You could just put all those files in the top, or all those variables, just move them up. You wouldn't have to call that into a function.
Yeah, you could put all of this, for example, here.
There.
You could do that. It's your choice. I like this better because now I know exactly which registers correspond to my timer. You do another assignment later on. You just take this particular thing out, copy and paste it over to your next piece of code because you know that this one is the right one for a 1 millisecond clock. Now this is an example for a 1 megahertz CPU, right? But in our case we have a different clocking frequency, so you need to redo the calculations.
Is that ISR function predefined?
Yeah, so what you can do is you can again, so when we talked about ISRs, there's this a website where you find this whole table and you say, well, I want to, so you look in the data sheet and the data sheet says, well, you would like to write an ISR for something of this kind, right? But how do you know what this particular, how you should write this precisely? And you can look into that onto that website, and you're interested in a compare, in this particular functionality for timer 0 or compare A, and then you will find out for our MCU, the 328P, you see it in the list, and you notice that you will need to write this particular string, and now you write your ISR accordingly. And there are different kinds of interrupt service routines that each of them may have different names from one MCU to another MCU. So that's why you need a table to look them up.
So that's where the data sheet comes into play?
The data sheet helps you to identify what kind